In the last video, we looked at something called a rate law. It's an expression that shows how the reaction rate depends on the concentration of the initial reactants. I get that it's something new, that you've never done this before. It looks totally odd and foreign. But as we go through these next two examples, I think it's going to start to click. You'll see some common patterns and trends, and this really isn't that bad. This is a pretty typical set of information that they might ask you for in terms of a kinetics experiment. We want to determine the rate law, the overall reaction order, the value of the constant, and the units on the constant. So we've got some data, the initial concentrations of each reactant, and their corresponding reaction rates. The rate here is listed as moles per liter second. Just to be aware, you could have this written a couple different ways. You might see like molarity instead of moles per liter. Seconds might be SEC. Any of that would be fine. It's a change in concentration per time. So let's attack this thing. Let's figure out the rate law. Rate law expressions always kind of follow a typical pattern. So here's the rate law. R, the rate, always equals a constant times the concentration of your reactants. So this bracket symbol means molarity or concentration. And now eventually we're going to raise that to a power. That power is called the order of the reaction with respect to ammonium. It's a whole number that kind of shows how changing the concentration of ammonium affects the reaction rate. We'll get that in a minute from the experimental data. Now the other reactant is that nitrite ion, NO2 minus. But notice in the data table it says NH2. I'm assuming that's a boo-boo. That's got to be a typo. It should be NO2 minus. And again, we'll eventually figure out the order of the reaction with respect to nitrite ions. So let's pick the ammonium first. I honestly do this by inspection. I know in the last video they kind of show how you can take two trials of data and sub that data into the rate law, and you can cancel like terms and simplify, and you can algebraically solve for the exponent of the ammonium. I don't do that. I just do it by inspection. I want to find two trials of data where the concentration of ammonium changes and nitrite stays the same. So what if we did, let's see, maybe 2 and 3? Here the ammonium doubles, but the nitrite stays the same. And then I ask myself, how does that affect the reaction rate? And just by inspection, I can tell them that the rate has doubled. If you double the concentration and you double the rate, that's first order. So I just put in a little 1 here. If you wanted to algebraically solve for that value of the exponent, you would take those two trials of data, you'd plug in the data into the rate expressions, and you'd compare them. And it would simplify down to something like 2 equals 2 to the nth power. I doubled the rate, I doubled the concentration of ammonium. Nitrite stayed the same, so eventually it just cancels out, along with the constant. Well, then that power needs to be a 1. But I just kind of remember it conceptually. If you double the concentration and you double the rate, it's first order. If you triple the concentration and you triple the rate, it's first order. You'd have something that looks like 3 equals 3 to the nth power. N equals 1. Now I do the same thing with my other reactant. I find two trials of data. I want nitrite to change, but I want ammonium to stay constant. So how about trials 1 and 2? We double the concentration of nitrite. The ammonium stays the same. And it looks to me like we doubled the reaction rate again. First order. These are both first order. If we double the concentration of one particular reactant, we double the rate. There, that's it. That's your rate law. Most of it is just kind of a plug and chug kind of thing. You just plug in the concentrations of your reactants. The only thing that you have to get from the data are those orders or those exponents. The next thing they were asking us for is the overall reaction order. Overall reaction order. Now this is the one that I think is kind of useless, and we'll talk about it a little bit later on. But all you have to do is add those individual orders of the reactants. So we add 1 plus 1 equals 2. I told you this wasn't going to be so bad. There's the overall order of the reaction. It depends on how many reactants you have. It depends on the individual orders of those reactants. But all you do is add them up. So then finally, we need the value of the constant and units on the constant. Now that we have our rate law expression completed, you can pick data from any trial, plug it in, and solve for K. So here comes the rate constant. Rate constant. I don't know. I usually pick the first trial. I don't know why. Arbitrary. I guess it just comes first. So let's say I pick trial 1. The rate is 1.35 times 10 to the negative 7th. And that could be like change in molarity per second or moles per liter second. Equals K is what I want to solve for. Then I'm going to plug in the concentration, the molarity of ammonium in trial 1 is 0.001. Oopsie, 0.100. Hello. 0.100. That's going to the first. That's for the ammonium. And then I do the same thing in trial 1. Nitrite is 0.0050. Yikes, I think I can squish it in. That's going to the first power. That's for the NO2 minus. Now you really just solve this, plug it in your calculator, and see what you get for K. For sig figs, I don't know, maybe 2 or 3. Technically, that nitrate 0.0050 is only 2 sig figs. So maybe I'll just put 2. K equals 2.7 times 10 to the negative 4th. So numerically, there's my value of K, and that should be constant. You can pick any trial of data. Plug it in the exact same way. K should be constant. Now, the sucky part is the units. Again, I find this just annoying. It's not difficult. It's just annoying and useless. I'm not going to use it for anything. I want to know that the constant is constant, and eventually we'll kind of look at graphs of constants, but the units to me are kind of irrelevant. I think here's the best way of solving for the units of the constant. Plug everything in to that rate expression with just the units. So I might do this as like, okay, this was molarity per second on the rate equals K times molarity to the first and molarity to the first, which together are like molarity squared. So I'm just going to do the algebra. I'm going to solve this for K with just the units. So I could do something like molarity per second times 1 over molarity squared, or like divided by molarity squared. That should equal K. I can simplify this a little bit. I got molarity on the top. I got a molarity on the bottom. And now there are a few different ways that you could report this number. Or this unit, I guess we'd say. You could say the unit is 1 over seconds times molarity. Or you could have molarity times seconds. That would be totally fine. You could show this as like seconds to the negative first times molarity to the negative first. That would be totally fine. The other option, technically molarity is moles per liter, but now we've got the inverse. So you could also say like liters per mole second. You could do that. It's like the inverse of molarity, moles per liter per second. Any of those would be acceptable units for your constant. Done. Yeah, that's not bad. That's all they could possibly ask you about this kind of data. You're building confidence, I hope. Let's try one more. The second one. Let's do all the same things. We'll get the rate law. We'll get the order of all three reactants, the overall reaction order, the constant. We'll put units on the constant. The whole shebang. This is a reaction with three reactants. Ooh, tricky. Oh, it's not going to make this any more difficult. We're going to attack it the same way. Let's get the overall rate law. The rate law. Or again, sometimes it's called a rate expression. Same thing. It always kind of follows the same setup. R equals K, my constant, times the concentration of my first reactant, which is bromate. And then experimentally, I'm going to look at the data and figure out the order of this reaction in terms of bromate ions. So I want to find two trials of data where bromate changes and everybody else stays the same. So maybe trials 1 and 2. This doubles the concentration of bromate while keeping everybody else constant. And I just ask myself, how does that affect the reaction rate? The rate doubled. If you double the concentration and you double the rate, this is first order. We'll say that's a 1. All right, so we do the same thing with bromine ions. Br minus. We got to find some data. We want bromine to change and everybody else to stay the same. How about trials 2 and 3? Bromine doubles and the other two stay constant. So we ask ourselves the same question. If I double the concentration, what happens to the rate? And by golly, it doubles again. So this exponent is like a 1. Because again, if the rate doubles, and if you wanted to plug all this data in and like compare rate laws, you'd have something that simplifies to like 2 equals, we doubled the concentration, and then it goes to some power. Well, if you double the rate, this is rate, and this would be like the concentration of, bromine or bromate or whatever ion you're looking at. If you double the rate and you double the concentration, that exponent has to be a 1. And the last one, the hydrogen ion. Okay, hydrogen. Let's look at maybe 1 and 4. We double the concentration of hydrogen while keeping the other two constant. That's the trick. The other two have to remain constant. And then we see what happens to the rate. Ooh. When we doubled the concentration of hydrogen ions, the rate goes up by 4. We quadrupled the rate. So now you're going to have something that kind of looks like this. The rate goes up by 4 when we double the concentration. Now this is for hydrogen ions. And again, now we just ask ourselves, what's the value of N? And advanced math, it should be a 2, right? This is second order. Hydrogen ions, you are second order. Second order means you double the concentration, but you quadruple the rate. Or again, you might find something like you triple the concentration. The rate goes up by 9, an exponent of 2. You quadruple the concentration, and the rate goes up by 16. That exponent is a 2. So again, I didn't like sub into the equation, cancel like terms and all that good stuff. I just did this by inspection. You find two trials of data where one concentration changes, the others stay the same, and you look at how that changed concentration affects your rate. If you double the concentration and you double the rate, first order. If you double the concentration and you quadruple the rate, second order. So now my overall reaction order, is just the sum of those individual orders. 1 plus 1 plus 2 is 4. Shocker. There it is. That's it. And then finally, we want the value of the constant and the units of the constant. So now that we have our rate expression and we know these orders, you can, again, pick any trial of data, sub in, you've got the rate, and solve for K. So, I don't know. Again, I usually pick the first trial, just, I don't know, because I can. So this will be the value of K, the constant. Okay. So for trial 1, the rate is 8.0 times 10 to the negative 4th. And that would be like molarity per second equals bromate 0.10 molar to the first. That was the BrO3 minus. Times bromine 0.1 molar to the first. That was for the bromine. And hydrogen, well, what do you know? 0.1. That one's going to the second power. That was for the hydrogen. You just plug this in your calculator and solve for, whoops, I forgot to put it in. K. I'll get that in there. K. There. Now we can solve for K. All right, so let's see what we get. The value of K is 8. Maybe I'll say 8.0. Then I got 2 sig figs and everything. And again, if you pick trial 2, 3, 4 and subbed in correctly, you should get the same value of K. The constant should be constant. Okay, so now the fun part, the units. So we're just going to set up this expression. We'll simplify it so that it only shows the units, and we'll algebraically solve for the units of the constant. Okay, so I would have had something that looks like this. Molarity per second, that's the rate, equals K times molarity to the first, molarity to the first, and molarity to the second, which obviously then this would kind of simplify to molarity to the 4th power. Okay, so we want to simplify this. And so maybe I would have something that kind of looks like molarity per second times 1 over molarity to the 4th, multiplying those. And I might want to simplify it then, and maybe I'd cancel out this guy, and I could reduce this down to a 3. And I think that's the best I can do, huh? So my units could be reported as like maybe 1 over seconds times molarity to the 3rd. Or maybe you'd have like seconds to the negative 1st, molarity to the negative 3rd. And obviously they could be in either order. You could have the molarity first, the seconds last. It wouldn't matter. Either of those would be acceptable units on the constant. So again, the units on the constant will depend on the expression. How many reactants? What are the orders of the reactants? So you really do have to kind of treat each case separately, each reaction separately. But I think that's the best way to do it. Simplify your rate expression, your rate law, to only include the units. And then just solve it algebraically for the units on the constant.